Okay, let's begin. So last time, what did we do? Okay, so last time, what we wanted to do, we wanted to solve the rate problem. So some things we notice, one, at least for straight lines, slope was connected to rate of change, speed. Or more specifically, how one thing, i.e., how one quantity changes in relation to another, right? So we looked at that example where you had that object that over 3 hours it traveled 150 miles and the slope was 50 miles per hour. And basically how you could interpret 50 miles per hour, what does that mean? It means that distance changes 50 times faster than the time units in this example, right? So when you say 50 miles per hour, what are you really saying? Well, for every 1 hour movement in time, there's a 50 unit movement in distance. So how can you say that? Well, the distance is changing 50 times faster, right? So if I had to look at distance and time as two separate quantities, I'd be able to say distance is faster. How much faster? 50 times faster, right? That's another way you can look at speed. And we saw that slope was one way we could do that. So then the next thing we saw, we wanted to generalize this idea. Right? And so now the question was, how do we apply this to non-straight lines? How to apply to, let's say, curves. Right? So you have some curve, it's not a straight line. How can you apply the slope idea? Slope is something that we usually are used to talking about for straight lines. And the answer, surprisingly, is to think like a flat earther. So, the idea here is, yes, we might know things are curved, like we know the Earth is round, but at a certain scale, if you look around, it looks pretty flat to me, right? The idea is, if you zoom in, so the idea was to zoom in, right? So if I look at this curve, it looks like a curve now, but if I zoom in on this spot and blow it up, the curve starts to look straight if you zoom in far enough, right? So while it's like super curvy, if I zoom in, it'll start to actually straighten out. And so the idea is, what we want to do is we somehow, because we know how to deal with a straight line, is somehow let's create a straight line at a point of interest. That's dead. Let's somehow create a straight line at a point of interest. The idea being, when we zoom in, the actual curve and that straight line are going to be super close to each other, right? So the idea is, we want to construct a line that can closely approximate the curve and this is what's called a tangent line. Right? Now, there are, when you want to define such a line, and then we define the slope of the curve, what does it mean to take the slope of the curve? Well, the slope of the curve is going to be equal to the slope of the tangent line at the point of interest. Right? That was kind of the big idea. And then, how do we actually find such a line? Because to find a line, we need a slope and a point. Yes, I know the point of interest, but what is going to be the slope of this line? If we don't know the slope of a line, the only other way to find a line is if we had 2 points. And so that's what we kind of did last time. We had 2 points, and because we only care about one of them, the idea was take this point and move it closer to that point, so that when we're drawing this line through 2 points, it's kind of like drawing the line through 1 point, the point that we actually care about. And to get that done, we used a limit, right? And so last time what we learned is how to find the slope of such a line, this line that's going to approximate our curve. And we'll get to the approximation idea in a couple classes, but for now, let's just run with this. And last time we found how to find the slope of this line. Last time we saw how to find the slope of this line. Okay. Namely, the slope of the tangent line at x is given by the limit as h approaches 0 of f of x plus h minus f of x all over h. And that became a very important quantity to us. That's a very important limit. It allows us to find the slope of the line. Why is finding the slope of the line important? Because that allows us to find the speed, how fast the vertical axis is changing with response to the horizontal axis. And being able to do that, we'll be able to apply this idea to a curve. So that's a very important. So this is muy importante. You have to say it in multiple languages to really get it. So the point, what we're going to do now is, I don't want to have to write out slope of the tangent line every single time. So we're going to write down some notation, and while we're doing that, give it a cool name to boot. So the notation for this idea. So remember, there are 2 guys that were really credited with the development of calculus. So there's Newton's notation. It's in fact called the prime notation, Newton's prime notation. And we have the Leibniz notation. So Newton, the brilliant British scientist, and Leibniz, the brilliant German mathematician, independently invented calculus, and they used different notations for it. This one was F prime. You have this little notch, it's like an apostrophe, very ostentatious apostrophe. Like if you actually look in the math textbook, it's not actually an apostrophe, it's more like a notch like that. It's very, of course, when you're writing it down by hand, you're going to write like a little stroke. It's called Newton's prime notation. So this is gives you the slope of the line at x. So if you have a function f of x, the function that measures the slope at x is given by this notation. And here, if you have like y equals f of x, Leibniz actually called it dy dx, right? And that was kind of like a change in y or a change in x idea, right? So your normal slope, so slope equals, so slope of lines, you can normally think of it as change in y over change in x. This is usually used with the Greek letter delta, but when you want the slope of a tangent specifically, slope of tangent line, you decide to go with the English letter D, dy dx, but it's the same idea. He was thinking of a change in y over change in x. Y is overrun, y2 minus y1 over x2 minus x1, which is in fact the difference quotient, but it's a difference quotient with a limit attached to it. And so you decide to change the notation like that and write d's instead of the delta. But those are the two main notations, and we'll talk about how we can actually modify these notations as we move on. But that leads to a very important definition. This important definition. Let f of x be a function. We define the slope of a tangent line to f of x at x to be f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That's an important equation. I need to know that. I'm actually going to ask you about that on the next quiz. Define provided the limit exists, because of course it's possible for the limit to not exist, and we'll talk about that, provided this limit exists. And now we call this limit. Now, normally math people are horrible at naming things. Well, not horrible, they're not very creative. We just kind of name it, the description of the thing that it's doing, right? So, but this time they threw out all the stops and they decided to get creative. We call this limit the derivative of f of x at x. Call it the derivative. Now usually in math people, they just name it. Want the name of a property, that just means you can continue drawing the function. Continuous? Hey, I found this theorem that says this y value will attain all intermediate values. What do we call it? Intermediate value theorem? Hey, we find this thing to find the slope of a tangent line. What do we call it? The derivative. They just somehow, what does the word derivative even mean? That's what they call it, the derivative. This notation, this limit is called the derivative of x, right? So f prime of x, this is red, f prime of x, right? So that because this little notch here is called a prime, and what you can think of it as, it is the derivative of f of x. Oftentimes when they want to say the x is the independent variable, they'll use the phrase with respect to x, meaning the x-axis is the axis with the independent variable. And sometimes this will be abbreviated. We don't always write out with respect to, you might write WRT. Right? So whenever you see that notation, you would read it on the paper, f prime of x. What does it mean? It's the derivative of f with respect to x. What does that mean? It's the slope of the tangent line. To f at x. Or, in other words, we actually define it to be the slope of the curve, slope of f of x. Right? It's the slope of this curve. Another way you can interpret it, how fast f of x changes in relation to x. So if someone says, when x moves by 1 unit, how many units will f of x move by, right? The answer to that question is the derivative. The derivative is going to tell you. So these are some important interpretations, I would say. Now, when you look at dy dx, it means all the same things, but in fact, that's how it's pronounced. So let me just say that. and a lot of people probably won't say this to you, but I'm going to tell you the truth. Sounding like you know what you're talking about is just as important as actually knowing what you're talking about. So you don't want to read math in a weird way. It's like, no one calls it that. No, you need to know how to say it. It's dy dx. That's how you say it. So I'll say dy dx. Everyone knows I mean dy divided by dx, and everyone knows I mean, oh, that's the slope of the tangent line. Right? So it's pronounced dy dx. It has all the same interpretations. And down here, same interpretations. Now that's going to be important because a lot of times you're going to have word problems where the derivative is going to be the thing you want to do. But you need to know when do you want to do it. Well, whenever you want to find out how fast one thing is changing compared to another, a derivative is probably going to be a good idea, right? And there are going to be these phrases here, they don't really show up, I guess, in real life, but in a math class they'll show up. Like there'll be a problem that specifically asks you, hey, what's the slope over here, right? And derivative, right? You can now think of that derivative is a synonym for slope. Now they mean exactly the same thing, right? It's a synonym, right? Now derivative does have the connotation that it's a more general version, like we can measure slopes for curvy things, not just straight lines, but it means slope, right? So if you're ever in a situation, I need to find the slope of something, the derivative is what you're going to try to find. Or if you're ever in a situation, I want to know how fast this thing is moving compared to that thing, then what you want to do is create a function that connects these two and find a derivative. And that's essentially how we want to solve the rate problem. Now, let's actually do a computational example. And this is usually one of the first examples in almost every textbook. They use this as the first example. They start out with the function x squared, because anything any simpler than that function is kind of silly to actually work with. Here, this is complicated enough for you to see something happening and be slightly wowed by it, and then at the same time, it's not so complicated that you're going to get lost in the complication and not know what we're doing. X squared is a pretty nice function to actually start out with. Let this be f of x squared. Here's what I want to do. Find the tangent line to f of x at x equals, or let me just break this up. Find the slope of the tangent line. At, say, x equals 4. And I'll follow up b, or find the equation of this tangent line. And full disclosure, on test 1, I'm going to ask you a question like this. It's definitely coming. You can expect it for sure. I'm going to have a function. I'm going to say, hey, use the definition of the derivative to find the slope of a tangent line. And then part B, find the equation of the tangent line. It's definitely coming. Okay. So let's deal with A. How do you find the slope of the tangent line? This means we want f prime of x. And what is f prime of x? Well, it is the limit, as h approaches 0, of f of x plus h minus f of x over h. So now we're going to go through and we're going to compute this limit. Okay, so if my f of x is x squared, what is f of x plus h?
X plus h squared.
X plus h squared. And f of x is x squared all over h. How do I find that limit? Step 1, try to plug in. You can't plug in h equals 0 because you would divide by 0. Step 2, try to simplify. Can we simplify? What would you try to do here? What can we do? me simplify this. Yeah?
You can do x plus h times x plus h. But
Yeah.
you should leave that
And what
part.
would you get?
X squared plus 2xh plus h squared.
Now the x's cancel.
Factor
So now you have the limit as h approaches 0, and you have 2xh plus h squared all over h. You can cancel this h, right?
factor.
Can't cancel. Cannot cancel that h. So that's 2xh. I was going to see who said yes. I could just like throw the marker. The next step would be to factor out an h, because you cannot cancel across sums. Now you can cancel. So now you can plug in h equals 0, and you get 2x. Now, something I want you to appreciate about 2x. Okay? So when we say, so this is not a part of the problem, but when f of x equals x squared, and you say f prime of x equals 2x, what are you saying? What is 2x? I want you to realize that 2x is a formula that gives the slope of the tangent line. To f of x at any x value. So in particular, slope of tangent line at x equals 4 is going to be equal to well, it's going to be f prime evaluated at 4. So this is something that gives you the slope in general, and we'll talk about that more as time goes on. But in this case, I want to know what is the slope at 4 specifically. So in other words, I need to find f prime evaluated at 4. And this tells me that f prime at 4 is equals 2 times 4. It's going to be 8. 8 is the slope of the tangent line at 4. Okay, B. Let's see who remembers our algebra. How would you find the equation of the line?
Y equals mx plus b.
Y equals mx plus b. What is the m?
The slope.
Right, so this is y equals mx plus b. M is the slope. How do we find the slope? What is the slope? 8. Derivative is synonymous with slope. Whenever anyone says slope, derivative, it's the same thing. So the slope, that's the derivative. Now, of course, you're going to need to find everything else. So now that we know the slope, what else do we need to know about this thing? So here we know that the slope is f prime of 4, which is 8. That's going to be my m in this, this scenario. How do I figure out the b? What do I need to know?
On f of x.
You need to know a point. What point specifically? Well, we need the point when x equals 4. So the slope is important. We also need to know a point. Now the point is when x equals 4, what is the y coordinate?
16.
It's going to be 16. Y is going to be 4 squared because it's x squared. So it's going to be 16. So the point is 4, 16. So now you want the line that has slope 8 passes through the point 4, 16. So what you're going to do, well, that's y minus y1 equals mx minus x1. Y minus 16 equals 8, x minus 4. And that would be your tangent line. Or if you wanted to write it in y equals mx plus b form, which I asked for, of course this is 8x minus 4 times 8. It's 4 times 8. Huh? 32 plus the 16. So this becomes y equals 8x minus 32 plus 16. Huh?
Minus 16.
Minus 16. That's our tangent. Now, what does that mean? So, first of all, any questions so far? So, we want to find the slope of the tangent line. We know that this is the formula that gives the slope of the tangent line. Very important formula. You need to memorize that. Pretty much every time you want to use this formula, copy it down. Copy down the general form before you start plugging it in, so it's seared into your brain. Okay. So, we want to find the slope of the tangent line at 4. How do you find the slope of the tangent line? That's the derivative. That's f prime. That's this definition. Go through, compute this definition, and at this point, we're all experts at limits, so this is not going to be a problem. Okay? We're going to get to an answer here, which is going to be a function. It'll probably be something in terms of x's, right? Then, at the point of interest, you're going to plug that in, and that is how you're going to find the slope at the point of interest. Now, if you want to find the equation of the tangent line, and there will be times when we want to do that, you need a slope and a point. That's how you can find the equation of a line. You either need 2 points or a slope and a point. We don't have 2 points, we have a slope, and we can figure out a point by plugging into the function. So we figure out the m by plugging in the x value into f prime. We figure out the y by plugging the x value into the original function. That gives us the point, and now with the point and the slope, we can find the equation of a line. And what is that saying? So basically, this is saying so we have our graph here to actually just see what's going on. So we have y equals x. And someone asked, okay, let's say x equals 4, right? So you're at this point. That's a point of interest. Now when you're at 4, this is at 16. This is a lot of real estate for no. Okay. Now someone says, okay, I want you to find the equation of the tangent line to that function at that point. Basically what you're looking for is the straight line that looks like this. It passes through that. Right? You want to find the tangent line. What is the tangent line? That's the line that when you start zooming in, the more you zoom in, the less you can tell the difference between that line and the actual curve, x squared. Right? That's the line that we just found. The equation of that line is 8x minus 16. It will be the line that passes through minus 16 over here, because that's going to be the y-intercept, with slope positive 8. Now, one way, there are a couple of interpretations you can take from this. One thing you can say here is that if this were measuring some quantity, right? So let's say I put an interpretation on these axes. That's distance, that's time. What I could say here is that at this point in time, the speed at which we're moving is 8. Right? I'd be able to say that, right? And essentially, speed is going to depend on the interpretation that's chosen for the axes, right? Now, we need to know how to deal with functions, but especially for applied mathematics, applied calculus, the functions themselves are less important than the interpretations that we're putting on the variables. That's where math really starts to become useful. Once you start, it's not just x and y, it has some meaning. That's distance, that's time. Once you apply meaning, now you can start to reinterpret all the mathematics in terms of some real world application, right? So yes, we figured out a way to draw this fancy line to this fancy curve, but it actually means something. We can take away information from that. That's going to be important. We can know how fast things are moving by doing that. As well as we can do approximations. We're going to do a section on approximation, so we'll get to that. But just so you can visually see what we just did. Someone gave us a curve, and we figured out a line to that curve that at the point 4, that line is going to be a really nice line to use. And it's worth mentioning that any other line would not have worked at the point 4, not as well as this line, right? And if I took any other line at any other point, it won't be a good approximation for that point, right? A different line would happen here. But the important thing that the derivatives tells us, no matter at what point when you want to construct a line, I know how to find the slope. It's going to be 2x, right? So I now found a general way for this curve, y equals x squared. Any point where you want to construct such a line, because that's a point of interest to you, 2x is going to be the slope of that line. Whatever your x value is, 2x. So if someone wanted to come, okay, what if we're minus 6? What is the slope of that line right now? Minus 12. Right? What if we're at 0? 0 is the slope. What if we're at minus 1? Minus 2 is the slope. What if we're at 10? 20 is the slope. I can immediately respond with the slope, because the derivative gave me literally a formula. It gave me a map to how the slope is behaving. Let's actually... So, and yes, we will get a lot more to interpretations later on, but for now I want to make sure we have the computational skills down. So I just want to do a few more examples. Just to make sure we know the ins and outs of how to actually do the computation. And interpretations are taken care of by later sections. So use the limit definition to find the derivative of A. Let's say our function is a constant, let's say C. B, suppose our function is the function a constant times x. Right? Like my function is 5x or 3x or 7x or whatever. Let's say our function is 1 over x. Let's say our function is the square root of x. Do I want to give any more examples? We'll stop there. So these are just going to be very basic ones as far as things goes. On a test, I'll probably give you a combinations of these and ask you how to do it. So on a test, I might tell you f of x is 2 minus 3 over x. Find the, or f of x is 2x minus x squared. Find that, right? But now let's deal with the individual functions, so we're just getting used to actually doing the computations. And we want to use limits here. Okay, so A, f of x is a constant. How do we find the derivative? Well, f prime is going to be limit as h approaches 0 of f of x plus h minus f of x over h. Write it down every time you want to use it, so eventually you'll remember it. Then it's really weird, but it happens. Every now and then, like on the first test, I ask someone to use definition of derivative, and they don't know the definition of derivative. Like, how do you not know the definition? Write it down every time. It shouldn't be the case that you got something wrong because you don't know the definition. That's not. Yeah. Okay. So know the definition. Make sure you can write it down. You can state it. You can. If I ask you, what is the definition of a derivative? You should be able to write that equation down. Okay. Now let's actually apply the definition. So if my f of x is c, what is f of x plus h? It's just the constant. It's just the c. There's no x to plug it in, right? Remember what f of x plus h means. You replace all x's with x plus h. There are no x's. So it's just c minus c over h. C minus c is? That's just 0. Limit is going to be 0. Does that make sense? Well, what would f of x equals c look like? Yeah? It's just a horizontal line, right? Passing through c. What is the slope of a horizontal line? Slope of a horizontal line is 0. Right? Now the value at any point, the y value, the output is going to be c. What is the slope of a horizontal line? It's 0. So our definition actually fits with what we know. Now, here's a short way to express this. Right, so at some point, I'm going to need you to just know what the derivative of certain kinds of functions are. Yeah, of course.
Yeah, so how can it have the same slope if it's only supposed to like hit it in one spot, if that makes sense? Because wouldn't it like run like...
Yeah, but for a horizontal line, any spot you pick, what is the slope at this point? 0. What is it over here? 0. The slope is going to be 0 all the time. It's always going to be 0. So here, it doesn't matter on the point. With x squared, it actually matters.
Yeah, that's what I was talking about.
Right, so over here, this line is actually steeper than this line. And the lines over here will actually have negative slopes.
Mm-hmm.
So the formula that's going to give me the slope of this one has to have a variable in it. It has to be able to change, right? So here, me telling you the slope is 2x. That x allows me to change how the slope is going to behave. But here, the slope is never going to change. It's 0 no matter where you are. It's a horizontal line, it's flat. There is no rise, it's just a run, right? Rise over run is going to be 0. It's always 0 at all places. Now, a short way to not find this, to write this. So eventually, like I said, I'm going to want you to know like formulas for certain functions, what the derivative is, and I might state them in the following way. I'm going to tend to use the Leibniz notation. So one way you can state this idea, if my function is a constant, its derivative is going to be 0. You can write it like this. d dx, you use the Leibniz notation. You write the function beside it. So in this case, I'm going to write c. And I say equals 0. That's how I can state it. So you would read this as saying the derivative of a constant equals 0. Right? More specifically, the derivative with respect to x of the constant is equal to 0, but we'll worry about that later. But I can state the conclusion as an equation. The derivative of a constant is 0. Yeah.
So instead of, like, if we knew that would be the answer, instead of doing all that on top, we can just write that and that would be
Yeah,
something.
there will come a point where I'm not going to ask you to prove it. You just need to know that that's going to be the case. You need to know, I'm looking at this, I know what the answer is going to be. You can write it out like this. The derivative of a constant is 0. Any constant. What's the derivative of 3? 0. What's the derivative of 5? 0. What's the derivative of pi? 0. What's the derivative of 17.9? 0. Doesn't matter what the constant is. C can be any constant. The derivative is 0. The derivative of a constant is 0. This is just a fact we know now. This is how you would write that fact down. The derivative of a constant is 0. That's just something we know now. What about constant times x? So it's not just a horizontal line, it's a line with some slope to it. Constant times x. So for example, y equals 5x. Or y equals 7x. Y equals minus 3x, right? How would I find, what is the slope of this line? What is the slope of this function? What do you think the answer is going to be?
Just C.
Should be just c, right? So we know it makes sense that the answer should be c. Let's see if our definition actually gets us that answer. F prime is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Limit as h approaches 0. Okay, so if my f of x is cx, what is f of x plus h?
C times x plus e.
C times x plus h, right? Replace all x's with x plus h. F of x is just c times x. Obviously, you can't plug in h equals 0, so we need to simplify. What do?
Expand, so
Can
C.
expand cx plus ch minus cx all over h. These guys die. Now we can cancel the h's. So now we have the limit as h approaches 0 of c. And I actually gave you a rule for that last time, right? One of the properties of limits, the limit as something approaches, x approaches a of a constant is the constant. Which is exactly what we expected to happen. That's actually good. So one way you can write this down is the derivative of c times x is c. Or something that's going to be important for you to know. If c equals 1, right? This is to say that the derivative of x is 1. That's something that you should know now. The derivative with respect to x of x is 1. Derivative of x is 1. A little bit more generally, the derivative of cx is going to be c. What's the derivative of 7x? 7. What's the derivative of 5x? 5. What's the derivative of pi x? Pi. Derivative of a constant times x is just a constant. And more specifically, derivative of x is 1. Derivative with respect to x of x is 1. So these two are pretty obvious. So that's just a horizontal line. It makes sense for the slope to be 0. This is just a constant times x. It makes sense for the slope to be c. But what is the slope of 1 over x? Now that should tell you that the answer shouldn't be constant, because 1 over x, that guy, he changes. Right, so if I'm at this point, the tangent line is steeper than if it's at this point. So the slope is definitely changing as we're moving along. But specifically, how is it going to change? Say f of x is 1 over x. How are we going to find the slope to this function? Well, same way we always do, Pinky. F of x plus, do you guys know about Pinky in the brain? Or is that reference to?
Might be.
It's borderline. It's definitely getting there. Like in another 5 years, like no one's gonna know what I'm talking about when I say that. Same thing we do every night, Pinky. That's the definition.
Yeah.
Write it down every time because I want to make sure I remember it. Okay, so if my f of x is 1 over x, what is f of x plus h?
Yeah.
1 over x plus h minus 1 over x all over h. How do we find that limit? Right, so this is simplifying a complex fraction. Quickest way to do that is to multiply and divide by the LCD. The LCD is going to be x times x plus h, x times x plus h. I'm going to take this guy, multiply that, and then the denominator, multiply the denominator. So if I take this times this, the x plus h's are going to cancel, and I'll just be left with an x. Minus, if I multiply this by this, the x's cancel, and I'd be left with an x plus h. Parentheses are important. And on the bottom, I'll have that. Now, of course, the x's are going to kill each other. We're going to end up having minus h over h times x plus h. H's cancel. And now I can plug in h equals 0. Minus 1 over x squared is going to be the answer. And so now, that's something that you know now. The derivative of 1 over x is minus 1 over x squared. That is a formula that will give us the slope at any point. Okay, try to figure out what it is for radical x by next time. And we'll move on.
Oh, we can have a quiz on this on Tuesday, yeah, right?
Yes. So quiz on everything up to here.
Including this?
Yes, everything this week.